Welcome back to ECE 501B. Today is the lecture immediately preceding exam number 1. Homework number 4 is due today. You can turn that in through the Dropbox or physically into the mailbox in the ECE building. I'm going to try to record a review session, and you'll hopefully be able to get that, access that on the D2L website. And finally, as a reminder, our first exam is coming up on Wednesday of this week, and it's actually at the class period at 4 p.m. on the 2nd of December. What I would like to do today is work through the following goals. I'll quickly go over the process that I'm setting in place for exam number 1. Then we'll get back into chapter 5. We'll review what we've talked about, and that will take us then into invariant subspaces. That definition will present a few facts about invariant subspaces. Then we will essentially define eigenvalues and eigenvectors. We'll find a few of those, and then we'll quickly walk through a method for finding eigenvalues and eigenvectors. The process for exam number 1, I'm going to allow you to have 2 sheets of notes. Those sheets need to be 8.5 inches by 11 inches, but you can use the front and back of those too. But that's really all you have then to bring to the exam, besides maybe a calculator and something to write with. But you will not be allowed to bring a textbook, no class notes. You will have those 2 sheets of notes, no cell phone, no cell phone, and no computer. In terms of the structure, it's still a little bit up in the air, but I'm thinking it will consist of 5 problems. Some of those problems might have multiple parts. There'll probably be at least one proof, more of a formal proof than the other classes of questions, which the other classes of questions might be to demonstrate or show or produce counterexamples. And there you'll want to use definitions or propositions and theorems to guide you in that process. Or you may need to find or create or build certain vector spaces, subspaces, direct sum decomposition, some basis, know the dimensions, maybe create a matrix from a linear map, talk about that linear map or that matrix, whether it's injective or surjective, possibly find the eigenvalues and or eigenvectors of that matrix or whatever it is that you're building. That's sort of the idea behind exam number 1 in terms of the type of questions you might expect. Let's return then, and the material really is coming for exam number 1. It's coming from chapters 1, 2, 3, and a little bit of the beginning part of chapter 5. And I'm assuming you can work with polynomials, which is chapter 4, and we won't explicitly cover chapter 4 material. Starting back up in chapter 5, from before we have this, or we know to anticipate that this is the equation that we're working towards, which is AV is equal to lambda V. V is a vector, A is an operator, and lambda is an eigenvalue. And really that V is an invariant subspace. It's one-dimensional, and that's what we want to try to get more comfortable with working through today's lecture. Quickly then reminding ourselves what happened last time. We examined several 2x2 matrices. We looked at a diagonal matrix. The eigenvalues were right there on the diagonal. We looked at an upper triangular matrix. Those real diagonal entries were also the eigenvalues. We looked at a dense or a non-sparse matrix that had a couple of real eigenvalues. And then we looked at this matrix C. that has a special structure, but we're not guaranteed that a real entried matrix will have real eigenvalues. This particular matrix C, if we opened up our field to be the complex field, it does have eigenvalues at -1 plus and minus J2. Those eigenvectors, though, are invariant subspaces, and that's a very important property that we want to understand after working through today's lecture. But the one thing we should note is even if you define a subspace or do a direct sum decomposition of some vector space, you're not guaranteed that that particular set of subspaces will produce invariant subspaces or vectors or subspaces which, when operated on by a linear map T, go back into the subspace that you began in or that the input vector was a part of. Last time we finished this particular example where our linear map was really a rotation in the xy plane. We started with 3 different subspaces. This is a direct sum decomposition of R3, the x-axis, y-axis, and z-axis. But for this particular linear map, which represents a rotation in the xy plane, which you can see if you simply study what x and y, how they are moving between the input vector and the output vector. If we start on the x-axis, v1, let's just say we're there at 3, 0, 0. After going through this linear map T, we do not remain on the x-axis after applying that linear map. We actually go to the y-axis when we operate using this linear map T. And for that reason, these subspaces that do form a direct sum decomposition of R3, they still don't produce invariant subspaces when operated on by this particular linear map. What I want you to realize then that these invariant subspaces are very special. This idea of a restricted operator, so we're restricting the operator to operating on a particular subspace. If that operator restricted on that subspace throws us back into the subspace that we started in, then we call that subspace an invariant subspace under this linear operator T. Let's now start walking through some of this. This was sort of where we had been. Let's now pick up with this notion of invariant subspace and move that all the way through to eigenvalues and eigenvectors. What are we meaning when we say invariant subspace? First, we have this linear operator T on a vector space V. It's taking the input space and mapping back into the output space, which is the same space V. Suppose that we now have identified a subspace U of that original vector space V. Then this subspace of V, which we're calling U, is invariant under T if we pick a vector that lives in this subspace U and we then operate on that vector through this linear map T. The result of that linear map from U through the linear operator T, if we remain in the subspace U, then that subspace is an invariant subspace. Or that is, this linear map T restricted to U, using some notation from before, is actually an operator. An operator, remember, is a linear map that goes from itself back into itself. In this case, we're starting in a subspace and we're returning to that subspace. We're not leaving that subspace when we operate on it through this linear map T. So T restricted to U is an operator on U. It's not just an operator on V. T restricted to U is actually an operator on U. The book actually has an interesting example of this process, and it's not with respect to matrices. It's actually dealing with polynomials. So let's look at this example from our textbook illustrating this invariant subspace property. Suppose that we're starting with a vector space V that's seventh order polynomials and everything is over the real number line R. And suppose that the linear map T is actually this differentiation operation. Now I hope it's clear that T, if you start with a seventh order or a polynomial that's seventh order or less, and you differentiate that polynomial with our differentiation operator T, that's actually going to return you to this same vector space of seventh order polynomials. So T is an operator on V. Now, consider the following. What if we restrict this operator on a subspace, and in particular, what if we make this subspace the set of fourth order polynomials? Well, I hope it's clear that U is a subspace of V. And what else can we say? Now, if we begin with a vector, a polynomial that belongs to this fourth order space, this space of fourth order polynomials, so if U, a vector, is in that space, if we now differentiate that polynomial, we're not going to leave that space, are we? We're going to stay in U. So that's actually saying that this subspace that's represented by the fourth order polynomials is actually invariant. Is an invariant subspace of the overall seventh order polynomial vector space under this linear map or operator of differentiation. Maybe as a way to get us thinking about what could possibly happen on the exam, what if we play with this idea of a subspace? Now, what is another subspace? Let's call it Q, that lives in this seventh order polynomial space, vector space, but we want Q to actually complete the vector space P sub 7 from this subspace of fourth order polynomials. what would we need to do to make that happen? Or does such a Q exist? On the exam, you would simply need to create or build such a subspace Q, and one such subspace would be this set of polynomials, let's say a to the fifth, z to the fifth. So now we're going up in order, polynomial order, z to the fifth. P sub 4 is just fourth order. Let's now go all the way up to the seventh order. And now, as long as those coefficients are independently available and live in the real number line, then that Q would actually complete the vector space of seventh order polynomials. Let's now look at some facts associated with invariant subspaces. I don't know if they're quick. Maybe I should just say some facts. Let's start with a linear operator T over a general vector space V. One is that the null space of that operator is a subspace, and it's actually an invariant subspace. If you start in the null space of T, you're going to get back to the null space of T when you operate on it with this linear map T. Likewise, the range space of T is also invariant under this linear operator T. If we start in the range space with a vector and we map that vector through T, we'll stay in the range space of T. And we're also going to find, or we'll show later, that invariant subspaces other than the additive identity and the entire vector space V do actually exist, depending actually on the field of numbers that you're playing with. If you're dealing with the field of complex numbers, then all you need is the dimension of V to be greater than or equal to 1. And then you will have invariant subspaces in that vector space. If you restrict your field of numbers to be the real numbers, then we've already shown that we might have a 2 by 2 matrix or a two-dimensional vector space that gets operated on by a linear map T that doesn't have real eigenvalues. And so it wouldn't have an invariant subspace because there are no eigenvalues. So we need the dimension of V in general to be bigger than 2 to be guaranteed a invariant subspace when we're dealing with our field being the real numbers. Let's now dig deeper into this, knowing where we are headed. Which we know that we want to be building up this notion of eigenvalues and eigenvectors, and we've seen that we can create one-dimensional vectors that are invariant subspaces. And let's now look at or study that particular idea. And the reason we want to do that is because this actually is the simplest kind of invariant subspace that is interesting to study. What does it mean to have a one-dimensional subspace? Suppose we are given a vector u in V. So this is just some generic vector in V. And suppose that we now create this subspace U out of that vector. Then the subspace is really going to be any scalar multiplication of that single vector, which U then is made up of all the scalar multiples of U. Now, if U is invariant, so what happens if this subspace U is in fact invariant? What does that mean? Well, now if we're given any vector, let's say W, that is in that subspace U, if we now map that vector, input vector, through the linear map T, if the subspace capital U is invariant, then this output vector needs to stay in the subspace U. Which really says then that by definition of how we created the subspace U, TW must be a scalar multiplication of this original vector W. Which says then that TW, if it represents if capital U represents an invariant subspace, then TW must be equivalent to some scalar lambda times the original vector W, where lambda belongs to our field of numbers, F. And this is what we expected, and this is what we've already talked about and we've already defined, but now we are hopefully in an even stronger position to say that we can call lambda, this scalar, an eigenvalue of this linear operator T if there is a non-zero vector W such that operating on that vector W with the linear operator T is simply going to be staying on that vector with a scalar multiple, meaning this relationship is true. If that relationship is true, then lambda is an eigenvalue. And I think you can anticipate then that this vector W is actually called the eigenvector and it is paired up with or associated with this scalar lambda. So lambda and W are very closely related. They're the eigenvalue eigenvector pair for this particular linear operator T. A 1D invariant subspace of T only exists if we can actually find an eigenvalue for that operator T. Only exists if T has an eigenvalue. As we saw with our matrix C, if we were playing in the real number line, there's not even a two-dimensional subspace for that for real eigenvalues because that particular map C did not have any eigenvalues associated with it. Now once we have this eigenvalue eigenvector relationship, we can actually manipulate that many different ways, and we've already looked at this a little bit, but we have this eigenvalue eigenvector relationship given by TW is equal to lambda W. If we now move the lambda to the other side, and now we will want to put this placeholder of an identity matrix scaling the lambda so that we can actually subtract lambda from a matrix T, then we have this relationship also. And I hope then, knowing what we know about vectors and this particular equation, now we have a matrix times W mapping us to the zero element. And anytime that happens, then those vectors, W in this case, are in the null space of that matrix. So if we have the eigenvalues, then we can actually find the eigenvectors associated with that eigenvalue. Thus, the eigenvectors of T that are corresponding to this eigenvalue lambda are in the null space of this operator T minus lambda I. Or you could say that another way. This relationship also means these vectors, they are a subspace of the original vector space V, since the null space of any operator is a subspace of V. So now we can think in terms of these one-dimensional subspaces. So now we can think of invariant one-dimensional subspace let's say, so now we can think of an invariant 1D subspace as an invariant direction in the original subspace V. And vectors in this one-dimensional subspace they actually don't change direction when we map those through this linear operator T. So we start with vectors in a direction, we map those through this linear map T. If those vectors are eigenvectors, then that linear map T keeps those vectors in that same direction, and we're not moving away from or off of that one-dimensional direction in the original vector space V. Let's look at some examples, although we've looked at eigenvalues and eigenvectors before, but let's just look at a couple of examples here. Suppose that somebody says, you know what if we define a matrix T that's an identity matrix scaled by a scalar A? What do we see relative to this structure, and what kind of eigenvalues and eigenvectors do we have for such a linear map? Well, our eigenvalue equation says that we have TW is equal to lambda W. So do we have any W's and lambdas that satisfy this relationship for this linear map AT? Well, if we now use this transformation in place of T, we have AI times W is equal to lambda W. And now we want to see, are there any values of lambda and W that satisfy this relationship? But if we look at what happens when we operate on a vector W through this identity map I, then we actually see that we have AW is equal to lambda W. And in fact, for this identity map that's scaled by A, the only eigenvalue is that scalar A. No matter what we do, lambda is only going to be equal to A. And W could actually be anything. So let's see if we can write that down. Only eigenvalue is lambda is equal to A in this particular linear map. And that eigenvalue is true for any vector in our original vector space V, or that says that all vectors in V are in fact eigenvectors. Which means that if we're mapping through the identity map, this is what we would expect. We're not changing the direction of the input vector that we started with. The direction of any vector is left unchanged by the application of this particular linear map T given by A times the identity map I. That's one example. Let's look at another example. Suppose now we have a linear map operating on a two-dimensional vector W1, W2, and now let's say that it takes W1, W2, and you could think of this as X and Y. You can take those two coordinates, and now you take the negative of y and put that into where the x coordinate is in the output, and you take the original x coordinate and move that to the y location. And if you sort of look at this, this is another example of a rotation in two-dimensional space. Let's now just look at W right now being some generic vector. It might be a real vector or a complex vector. Let's just keep it general and say it's in F2. Or W is now W1, W2. And we want to know, what does this eigenvalue-eigenvector relationship imply? Well, TW just gives us that, so that's now on our left-hand side of this relationship. That's now minus W2, W1, and that's supposed to equal the eigenvalue lambda times the input vector W1, W2. That's by definition of the eigenvector. And that's linear map. So now what does that show? Well, now we simply look at the two different coordinates. If we look at the first coordinate in this relationship, we really have two equalities here. We have minus W2 is equal to lambda omega 1, and the second coordinate in this equality says that omega 1 is equal to lambda omega sub 2. And now what we can do is we can actually take and try to eliminate W2. We can take this and say, well, W2 is actually minus lambda W1, simply multiplying by minus 1 on both sides, and now use this value for W in this second equation. And what does that give us? That now gives us one equation involving lambda and W1. W1 is then lambda times minus lambda W1, or this is now minus lambda squared W1. And this actually then, if you look at what this says, you can think of, on the left, you have this identity element 1 times W1, and so for any value omega sub 1, you see that minus lambda squared is equal to 1, or that lambda squared is equal to minus 1. And now we can look at the two particular cases of our field of numbers. If our field of numbers F is the real line, then are there real numbers lambda, which when squared will give us minus 1? And we can see then that when we restrict to the real line for our field of numbers, this particular map produces no invariant direction. There is no eigenvalue and consequently no eigenvectors. We have no invariant directions, and that's because really we're doing these rotations, or it's just a rotation in the two-dimensional space. And anytime we're rotating, we're not staying in the same direction. This rotation then doesn't preserve any directions. What if we loosen the field of numbers up a little bit and we let it be complex? Then lambda squared equaling -1 does allow for a solution. Now we can say that lambda can be plus and minus j, plus and minus the square root of -1. That's what the j is symbolically showing. Now, once we now have these eigenvalues, they're actually complex, but now that we have these eigenvalues, we can actually build the eigenvectors from those. Suppose now we look at what the eigenvector is when lambda is equal to I. So now we're looking at the eigenvectors. Now we need to go back to these equations and replace lambda with what it's equal to. Here is our governing set of equations. We can now see that we have minus omega sub 2 omega 1 is equal to lambda, which is now I, times the original vector omega 1 omega sub 2. But this now gives us two equations that should give us exactly the same answer, since they're now dependent equations because they have a non-trivial null space. So this, if we just looked at the first coordinate, we would say minus omega sub 2 is I omega 1. Or if we started with omega 1, now we could just say that, or maybe I should say, what if we replace omega sub 2? Omega sub 2 is going to be minus I omega 1, just multiplying both sides by -1. So the eigenvector associated with this eigenvalue, lambda equal I, is going to equal W1, and W2 is minus I W1. So if we pick any arbitrary W1 from our complex field of numbers, then this is the eigenvector associated with the eigenvalue equal lambda equal I. What about the other case? What if we look at lambda, the other eigenvalue, which is minus I? Again, we can go back to our governing relationship. That was minus W2 W1 is equal to minus I W1 W2. Or we can now see that minus, looking at the first coordinate, minus W2 is equal to minus I W1. If we multiply both sides by -1, then we see that W2 is now just I omega 1. And now we can see then that the eigenvector associated with lambda equal to minus I is this vector W that will be omega 1 and omega 2 is I omega 1 for any omega 1 belonging to the complex field of number C. There's a couple then of examples of eigenvalues and eigenvectors. Let's look at, rather quickly, I'm just going to sort of read through a brute force method for finding eigenvalues and eigenvectors. There's some words here. I'm just going to present it, and you can then read it a little bit more at your leisure and figure out how do we generalize this approach that we just did, and I'll illustrate it with a second order example at the end. So how do we find, in general, what's a process or a method for finding eigenvalues and eigenvectors. And we want to do that without having to rely on computing determinants, because determinants are not until the last chapter of the book, and we don't want to go skipping that far ahead. So the idea here is we play with invariant subspaces, or that property, and that now allows us to create these concepts of eigenvalues and eigenvectors, and in fact, following that process through, allows us to find our eigenvalues and subsequently our eigenvectors. So now let's see what that does, and let's just assume, to start this method out, is let's just assume that we have an n by n matrix T. And we're going to assume then that we want to find the eigenvalues and eigenvectors for that matrix, capital T. So we're starting with the governing equation, Tx is equal to lambda x, and x has n coordinates. X sub 1 is the first coordinate, x sub 2 is the second coordinate, etc. And this relationship, Tx equal lambda x, actually creates n equations in terms of the n eigenvector coordinates, x sub 1, x sub 2, through x sub n. And if you multiply that Tx equal to lambda x out, you will then see that you do indeed get four n equations, the first equation being t11 x1 plus t12 x2, etc., equal lambda. And lambda is not yet known. We're trying to find what these eigenvalues are, so we want to leave lambda as a variable. Lambda times the first coordinate x1, and you do that for each of these n coordinates of your proposed eigenvector x. So now we have n equations in these n unknowns, x sub 1 through x sub n, where x sub 1 and x sub n are the coordinates of our eigenvector. Now what we do is we simply pull one of those equations aside. Let's just look at the first one and solve it for that coordinate, x sub 1. If we go back to this first equation, and if I subtract t11 x1 from both sides, then I will get or obtain an expression that has x2 through xn on one side and only x1 terms on the other side. And that's what I'm saying here. I now have lambda minus t11, that quantity times x1, and that's equal now to this linear combination based on the elements in the linear map T that scale all of these other coordinates, x sub 2, x sub 3, x sub n, of this potential eigenvector. Now we have x sub 1 in terms of the remaining n minus 1 coordinates of our proposed eigenvector. We now want to use that and substitute that. That was our first equation in this example. Now substitute for x1 in the remaining n minus 1 equations. Meaning in the second equation, use this relationship for x sub 1 and substitute it out. And now we have n minus 1 equations in terms of these n minus 1 coordinates, x sub 2 through x sub n. Then we simply do that again and again, all the way until we end up with just one equation, and that might be the x sub n equation, it might be x sub l, it depends on what you think might be a more optimal way to process this substitution or elimination process. But after all of that is accomplished, we will end up with this polynomial in lambda. Again, lambda is our variable that we are parameterizing our eigenvalue with respect to. We'll get an nth order polynomial of that times x sub n, and we want x sub n to be non-trivial, so x sub n, or x sub l in this case, is non-zero, which says that we are now forced to have that left-hand side, this nth order polynomial in lambda, and remember what t was. T was a linear operator that was of dimension n by n. That gave rise now to this nth order polynomial in lambda. Now let's set that polynomial in terms of lambda equal to 0 and solve for the values lambda that force that equation to be 0. And whether or not that is going to happen, as we've seen, depends on what the field of numbers are that we're allowing lambda to belong to. It may be that if we're dealing with the real numbers, we may not be able to find n roots of that nth order polynomial. Maybe they're all complex roots, and then we don't have any real roots of that nth order polynomial. If we're dealing with C, then we're going to have n roots of that polynomial. Now, for each of those roots, if they exist, we substitute that lambda back into the n equations in the very first step, and now we simply have n equations in n unknowns, and we can solve those because by definition of those lambdas, we've now created a non-trivial null space. We now have non-zero coordinates for x1, x2, x sub n that will indeed solve those n equations in the n unknowns for those coordinates, and that will now give us the eigenvectors for that particular lambda. Let's look at an example. That was pretty fast, but let's just see what happens if we work through, and this is a fairly easy example, but it gets a little bit more tedious as we get higher and higher dimensions on the matrix A. In this case, it's little n is 2, so we're looking at a 2 by 2 matrix. Ax equal lambda x. We now have our eigenvalue eigenvector relationship. We can create the first equation, 1/2 x1 plus 3/2 x2, by simply doing the matrix multiplication or matrix vector multiplication on the left. That's equal to the first coordinate, lambda x1. Likewise for the second equation. Now, if you remember what we were doing in the second step, we take one of those equations and we solve for one of the variables. What if we take the second equation and solve for x sub 2? If we subtract minus 1/2 x sub 2 from both sides on the second equation, we now get, when we divide through by that coefficient, lambda minus 1/2, we now have a relationship of x sub 2 in terms of x sub 1, associated with the coefficients of the matrix A and these unknown quantities lambda. If we now use this equation in the remaining equation that's left, we only had 2. We used the second equation to relate x1 and x2. Now let's use this x2, x1 relationship in the first equation to get rid of x sub 2. We now have 1/2 x1 is equal to 3/2 times x2. This is now x sub 2 from above, and that's equal to lambda x sub 1. If we do the algebra, let's subtract minus 1/2 x1 from, or add minus 1/2 x1 from both sides, and we now have 3/2 times that quantity in brackets equal to lambda minus 1/2 x1. If we clear the denominator expression on the left-hand side, which is going to then be multiplying by 2 times lambda minus 1/2, we end up with two terms that are the same. If we now distribute that 2 inside that parenthetical expression, we end up with 2 lambda minus 1 multiplied together, or that's now 2 lambda minus 1 quantity squared times x1 is equal to 9x sub 1. We want to now see if this particular expression in terms of lambda has a solution. That's what we do in step 5. We now solve, or try to find, values of lambda that solve that expression. We could either plug it into the quadratic formula here. Let's just move 9 to the other side, take the square root of both sides, And now we have 2 lambda equaling minus 2 plus 4, or our eigenvalues for that original matrix are now minus 1 and plus 2. Are we finished? Not quite. Now that we have the eigenvalues, now we can find the eigenvectors, and we can go back to our governing relationship from before. We had 3 halves x1 was equal to lambda minus 1 half x2. We're trying to find values for x1 and x2 that make this equation true, and we plug in the specific values of lambda that we've now identified as being minus 1 and plus 2. If we do it for the first eigenvalue, let's say lambda sub 1 equal minus 1, we now see that 3 halves x1 is equal to minus 3 halves x sub 2. We can get rid of or divide by 3 halves on both sides, and we now see that x1 is equal to minus x2, or if we want x1 to be our free variable, then we see that x sub 2 is minus x sub 1, and an eigenvector then associated with the eigenvalue at minus 1 is a minus a, where a is now any real number. And that's now an eigenvector. So you can see that these eigenvectors are not unique. You could normalize those. You could make them maybe nicer for your particular situation. We can finish this example by plugging in lambda sub 2 equal to 2 in the same expression that we used before. We now see that 3 halves x1 is actually 3 halves x sub 2. Dividing both sides by 3 halves, we see that x1 is equal to x2, or both coordinates are the same in our eigenvector. And so now we have, with b being any real number, we have an eigenvector bb for the eigenvalue lambda sub 2 equal to 2. I think that was enough information for this particular class. I should just note that this brute force procedure for finding eigenvalues and eigenvectors gets a little bit involved when we have a high order, or little n gets bigger than 2. But you now can see, I hope, or appreciate what the steps are in that process, and you can now understand how to find these invariant, one-dimensional invariant subspaces, if they exist, for given linear operators. And we'll pick up at that point after exam number 2.